So thank you very much for the opportunity, and I'm glad that you stayed to this time. Thank you. Thanks for the organizers for making this wonderful event possible. So I want to start in a different order. I want to first tell you a little bit about what kind of mathematician I am. And I'm going to start with the math, and I will end with the things a little bit about myself. So first of all, I need to tell you what kind of mathematics I do. And I have a feeling that many of you are not familiar with this type of mathematics. So let me introduce you with a few examples. So the first example is very simple to describe. So imagine you have 4 companies, and you have, or 4 factories, and you have 4 cities that demand laptops. So these factories produce laptops, and there is, those numbers that appear there represent represent the amount of laptops that are produced in each factory. For example, maybe Los Angeles produces 286, and then the demands are here. So for example, maybe San Francisco requires 220 laptops. So now the factories produce these objects that cannot be divided. Nobody wants to buy half a laptop, right? I mean, that's clear. But there is a cost of transportation. So maybe shipping a laptop from Los Angeles to San Francisco might be, I don't know, $30 in UPS. But if you ship to Santa Barbara, it might be, I don't know, $50. So every assignment of transportation you make is, has a price included into it. So the thing that you have to consider then is a very natural question to study the question of what is the best assignment of transportation that you can do to minimize the cost. So the cost in this case will be the sum of the cost of the assignments you gave. So maybe you decide not to use one of these arrows, but that's OK. So that will be cost 0. Is the problem clear? OK, so this is a very, very classical, I will say even one of the original examples of an area of mathematics, an area of applied mathematics called combinatorial optimization, which is essentially optimizing situations given finitely many options. So I am an expert on this field. And I will say that if you talk to anybody that works in this field and they see this problem, they will say, well, that's one of the easy problems. Why? I will explain that to you in a moment. Now let me go to another example that for many people that work in the area, they will tell you it's a hard problem. And that has to do, I'm going to explain it to you in a very simple version with, imagine there is a fancy planet where there's money of the following denominations. You have a 4, 6, and a 15. So this is the money that they have in this planet. So you can ask several questions if you are a member of this planet, inhabitant of this planet, is first of all, what amounts can you give with these coins? So obviously you cannot do a 5, right? Everybody see that? OK, so you cannot do a 5. So you can ask questions about what are the possible coin amounts or amounts of money that you can do with this. I remind you of the amounts 4, 6, and 15, right? Now, how many ways are there to give change, given some amount? So maybe, for example, you want to say 20. So you can do, let's go back for a moment. Oops. So if you want to, the amount of money you're giving change for is 20, well, then you have, you can give 5 4s, right? Or you can do 2 6s and 2 4s. That's another possibility. Yeah, everybody's with me? So there's many combinations you can do. And of all those possible combinations, you would like to know how many are there, exactly how many are there. And there is, of course, the most classical optimization situation when you would like to minimize the number of coins that you use. You just want to use as few coins as possible. So in this case, in both cases, the example I just gave you use 4 coins, but you can find examples, I'm sure, where you can see that with fewer coins, you can minimize the same amount. OK, how about denominations? The fewest number of denominations. The first example I gave you, 20. Well, you can do it with just one single denomination, right? So this is another example of minimization problem. And this corresponds to minimizing different norms, different types of objective functions. So everybody in this room has a preference, and that means it's an objective that you would like to maximize or minimize if you dislike something, right? So this is the general type of problems that I'm interested, and so I have been working on this. What they have in common is that if you take these problems and you look at them, you analyze them mathematically, they all look like this. You can describe them with a system of equations and inequalities, linear equations and inequalities. And in these two examples, you are literally working on the set of integer solutions of these systems of equations and inequalities. Okay? Are you with me? So this is the mathematical model that I care. It's very much about solving equations, but I have to solve them over the integers. Yeah? So it's very Diophantine if you want. Now, as I mentioned to you, these two examples are very different. The first example, the example of the factory, is a classical problem that goes back to the beginning of the field of combinatorial optimization, 1940. Koopmans and Kantorovich got the Nobel Prize in economics for analyzing that problem, and one of the reasons it's so important is because it belongs to the category of solvable in polynomial time. So computers can do it very, very fast, and the reason is it's almost like a miracle, but it's not a miracle, it's mathematics, that you can prove the following. So remember, we want to have integer values, right? Integer values. We cannot allow to have half a laptop or have 3/4 of a laptop. That's not legal. So nevertheless, get this. This is the amazing part. When you run an optimization routine called linear programming, there's many algorithms to solve that. They are among the fastest algorithms on Earth. They're very, very fast. And they are designed to solve this type of problem. Here you want to maximize an objective function, in this case a linear objective function, the cost, subject to some linear inequalities. When you do that, you are maximizing over real solutions, all the real vectors that satisfy these equations, okay? But guess what? You get integer solutions. So the optimal will actually be one of the corners of this polyhedral shape. That's the possible set of solutions. But the amazing fact is that in that example I gave you, you are actually going to get integer solutions. That's beautiful, right? It's the geometry of these objects that allows you to do that. So now, on the other hand, the other example that I show you, you definitely, again, so both of them can be modeled in the following way. You want to solve, maximize, or minimize a function that satisfies some linear equations on inequalities, and you want the solutions to be integer value, right? In the case of the coins, you in fact want not only integer, but you want non-negative, right? Nobody wants to have negative amount of money. So that's, but you see the possible solutions is a discrete set, it's a combinatorial problem. It's not a continuous problem. So you have an object like this where there's a discrete set of possible solutions. So again, as I told you, the amazing thing is in the first example, all the discrete solutions are on the corners, are finitely many of them, but they are already real. Solutions give you integer. Versus in the second example, the example of the coins, they are hidden inside. They are really in the interior, and it's very hard. You have to cut the fat out of the body of this animal to get to the solutions that you want. Are you with me? Yeah? Any questions so far? Now, this is in mathematical jargon. There is one thing to observe. So the first problem is what we call easy because it's polynomial time solvable. For example, using interior point methods or even network flow problems that we teach undergraduates. And on the other hand, the other problems fall into the family of problems that are called NP-hard. And it's one of the most, perhaps in my taste, the most fundamental problem in modern mathematics to try to understand the complexity of problems from the computer science point of view. And for this, we need tremendous amounts of new mathematics to be developed. But at the heart of this question, is it true that maybe all hard problems are just easy? But we don't know. We just haven't found it. We're just being stupid. So, but the fact is that the NP-hard problems is the biggest, we frequently find NP-hard problems. I gave you the example of the coins. The traveling salesman problem is another example, and so on. Okay, are you with me so far? Okay, what I'm going to do now is I'm going to tell you a taste of geometry, because I happen to be a person that believes that there's no difference between pure and applied mathematics. There's only emphasis that people put on subjects. So if you look at a lot of examples in the history of mathematics, people really look at mathematics in a very global way, but also, we just saw how mathematics can be part of the analysis of social systems, right? Of social justice as a driver of truth, as a driver of analysis. And mathematics deserves to also be diverse in subject too. So when you attack a problem, you deserve to use not just differential equations, but you also would like to use algebra, topology. We saw examples in the talk by Edgar when topological aspects have to do with motion analysis. So what I'm going to do now is I'm going to tell you about one geometric theorem. So this is a theorem in geometry that explains, first I'm going to explain to you in this side of the continuous version, the real value version, and then you're going to see that is really influential in the real value side, and then I'm going to try to tell you about the theorem in the integer side, okay? That's the plan for the rest of the time. So that's Carathéodory's theorem. Is one of my favorite theorems on Earth. So for that, I need to introduce something that is going to look familiar to you. How many here know about linear algebra? How many of you teach linear algebra? Raise your hand if you like linear algebra. Very good. I have lots of people that like linear algebra. Okay, you are in for a treat. If you like linear algebra, you're going to like this because it's all essentially a generalization of linear algebra. So I'm going to consider an object called a cone. So in linear algebra, we do vector spaces that are just sums of vectors generated. You have some basis of this vector space, and you consider all possible real linear combinations with positive or negative coefficients. Now here, all I'm going to do is I'm going to be non-negative. When I take a linear combination, just take non-negative values. That's all I'm going to do now. All right? And the set, when I had a vector space that was a set of all possible finite linear combinations of some set of vectors, here I'm going to consider, if I start with a set of vectors, all non-negative combinations, and that's going to be a cone. This is a cone, okay? It's like it's some kind of variation of the notion of vector space, and you're going to see it's very powerful. It has all kinds of very beautiful properties. So so in fact, it's not difficult to prove. I'm not going to do it here, but if you have a cone, you can see that like in vector spaces, something is a cone. If you take two elements in the set, you add them together and you still are in the set. And in addition, if you multiply by a positive scalar, you are still in the set. This is reminiscent of the exercises we give undergraduates to check that something is a subspace, right? So this is very similar. Okay, little quiz for the audience. What do you think should be the cones in dimension 1, in R1? So, for example, the 0 vector is a cone, fits the definition. So what else? Okay, we have also the entire line is a cone because you can have the vector 1 and -1, and in both directions you can go, right? And you can have half lines, right? You can have the from 0 to positive infinity or from 0 to negative infinity. You see that? So there's a very simple classification of all possible cones in dimension 1. Now let's go to a more higher exercise. Are you ready? Get your imagination hat out. You have 2 dimensions, and I give you 3 vectors, 2, 1, 2, 2, 2, 3. How does the cone look like? Looks like this. So it's every possible vector with real coordinates that it lies between these 2 vectors. So this is 2, 2, 1, and this is 2, 3. As you can see, 2, 2 is irrelevant in some sense because I can write it in terms of the other ones, but it's going to be important later. You're going to see why I'm allowing for the notion of redundancy here, as you will see later on. Okay, so how about this one? Here's a cone that is generated by infinitely many objects, infinitely many vectors. So I have all the vectors that are at level 1 and that belong to a circle, right? At level 1. So this is what does the cone look like? That's why it's called a cone, because it looks like a ice cream cone. Right? It's all the vectors that line infinite. I mean, it's an infinite cone. It's infinite ice cream, the best kind of ice cream. And you have that's a cone. Now, so my academic great-great-grandfather was Hermann Weyl. And so that's it. I'm biased, right? So I'm going to state this theorem as the Weyl-Minkowski theorem for a reason, right? So it's family reasons. So every cone can be represented. He's either by, every vector, every cone that is generated by finitely many vectors can also be explained to you, expressed to you, as a set of solutions of finitely many linear inequalities. So I'm giving you the example here. The cone that I gave you before, generated by 3 vectors, can also be explained by saying, well, is every vector that is on one side of this line and in this other side of the other line, right? You see, there's 2 lines that define the inequalities that define the cone. So this representation, either as rays of a cone, the generators, like usually in vector spaces, we have a basis type thing, or as you have a system of description and equalities and inequalities that describe it. This is due to both these gentlemen, Minkowski and Hermann Weyl. So now, I want to make a point to all the young people here. How often you see, oh, this is amazing mathematics. I'm sure, I'm not sure if I'm going to find a theorem like that myself, right? So I'm going to tell you something. There's so much open mathematics out there that you are sure to find a theorem with your name on it. I guarantee you. And just to show you how many open questions are there in this field, I want to introduce you to my favorite example of a cone, because there's so many open questions about this cone. And this is the cone of n by n magic matrices. So what's a magic matrix? It's an n by n matrix that you fill with real numbers, non-negative real numbers, with the property that every row sum, column sum, and diagonal sum is the same. So for example, here is 0 plus 2 plus 1 is 3, 3, 3. Everywhere you see is a 3. The magic sum is 3. Now, I'm going to prove to you, by the lemma that I showed you before, that this is a cone. The set of all 3 by 3 magic matrices is a cone. Here you are. So for example, if you guys give me a matrix that is in the cone, it's a magic matrix, and I multiply that by a non-negative number, well, the magic sum changes, but it's still a magic square. Similarly, if I take 2 magic squares and I add them together, I get another magic square. Are you with me? Everybody see that? So here is where remember my great-great-great-grandfather, Weyl-Minkowski theorem? So I describe a cone to you. How am I describing this cone? Do you see how I'm describing this cone? I'm describing this cone by linear equations. You see? The row sums and the column sums have to be equal. The diagonal sums have to be equal, right? So these are equations, linear equations. So there's a natural question. By the Weyl-Minkowski theorem, there has to be another representation. There has to be some kind of basis of the cone, like we teach in undergraduate linear algebra. So there's a natural question, yes. Is there a finite set of n by n magic squares that generate every possible magic square? By the way, this is a typo. Every possible magic square, not necessarily integer, but most people in recreational math like to do integer magic squares. I allow real magic squares for the moment. Later I will go integer, but okay. So the answer is yes, and ladies and gentlemen, here it is. These 4 generate every possible magic square, 3 by 3 magic square. That, in other words, no matter what magic square you come to give me, it's a 3 by 3, I will be able to write it as a non-negative integer, non-negative real combination of these 4 matrices. Is the fact clear? Are you with me? Okay. Open problem for the young people that are getting bored already, checking email or something. All right. So here you are. You can figure out. Can you figure out who the generators are for the n by n magic square matrices? This is an open question starting n equals 6. In fact, I will challenge anybody. I mean, I think it will be a fantastic, for example, maybe a pretty good master's project to figure out a really fast algorithm to figure out the 7 by 7 rays. In other words, the generators of this cone. I don't know the answer. all right? So there you are, lots of open problems for cones. We don't know that. Okay, but the fundamental application of cones is who are the generators? So I just show you that the problem of finding a basis for a cone is hard, right? It's not as easy as in vector and linear algebra. Now we are not in linear algebra anymore, right? So we are doing something much harder, and already the question is also how few rays, how few generators do you need of the cone? And okay, so that's the fundamental mathematical question, and this gentleman, Constantine Carathéodory, remarkable man, figured out exactly what the answer has to be. Now, before I tell you the answer he found, let me say that you are familiar with a very similar answer. So if you are in a d-dimensional vector space, what's the worst that can happen? How many vectors do you need to generate any vector in a vector space of dimension d? D, right? This is what we teach undergraduate linear algebra. This is kind of the main points. All right. Well, this guy he proved the same type of theorem for cones. So if you have a d-dimensional cone, in fact, even if it is infinitely generated by infinitely many vectors, you have a cone generated by the vectors in the set X, and now you give me an element of the cone, just one of the elements of the cone. Those elements that you use to generate the cone, you only need d of them. D of them suffice. Okay? Are you with me? So, for example, let's go back. Let's do an example with my favorite cone. What was my favorite cone? The magic square matrices, right? The 3 by 3 magic square matrices. First of all, what's the dimension of that cone? Well, it's a little exercise I'm going to leave to you guys. It's a 3-dimensional cone, actually. It's a square. It's a cone. So the way it looks, the 3 by 3 magic squares look like you have a square, and then you, from the origin is here, you put the square over there, and you make the cone go into infinity from there. Yeah? Are you with me? So that means that you have this 3-dimensional cone, okay? So 3 of these suffice. Even though I gave you 4 generators, no, in any circumstance, Federico gives me one of these magic squares, I only need to use 3 of those generators. But I may need to use them all, I may need to in different combinations of the 3 in different circumstances. All right. So, and again, Carathéodory's theorem is remarkable in optimization. Essentially, we want to understand solutions. Just like Rodrigo was talking about understanding solutions of differential equations, we are not any different. We would like to understand how the optimal solutions of these discrete optimization problems look like. And in this case, we know that the Carathéodory's theorem tells you how many generators are sufficient. That really tells you about the number of non-zero entries of an optimal solution. So let me state it to you in terms of the linear programming problem that I showed you at the beginning. So if you want to minimize a linear function over some polyhedral region described by linear equations and inequalities, and this leaves, you have I hope I didn't change the, I think yes. No, I think I'm fine, yes. So this is a d by n matrix, and I'm looking at this ax equals b set up. So in this case, Carathéodory's theorem tells me, if you think about it, this is really asking, is b in the cone generated by A? You see that? Because you want to write b as a non-negative combination of the columns of A. So it's the cone generated by the columns of A. So if you want to know, this cone actually lives in d-dimensional space, which is the space in which the columns live, right? So by Carathéodory's theorem, you will never need more than d vectors there. Yeah, so that tells you you can have an optimal solution which will really have d vectors or d non-zero entries that suffice. Now, one of the hottest things that happened in, let's say, the last 10 years because of image processing, MRI, mathematics made a big impact right here at UCLA. Emmanuel Candes and Terry Tao, who's a professor here, very well-known guy, they wrote a paper about the study of signal processing signals with few measurements, right? And in this case, this question of finding the sparsest solution, finding the minimal representations of an optimal solution goes to the heart of that, to the applications in signal processing. So you can ask questions, can I find, I just give you that, I give you $1,000, but can you please find the one that really uses the fewest possible number of vectors of the column vectors? In this case, I gave you the upper bound is D. It's an upper bound, but if you insist on finding the sparsest solution, that's an NP-hard problem, actually. And so a lot of the work that goes into signal processing requires finding sparse solutions, because if you're a toddler and you are taking an MRI, you don't want to have the toddler sit there for half an hour. They cannot sit for half an hour. So you want to take few measurements and then comes to recover the signal completely. So these are extraordinary challenges for applications, and they have real impact, but they come from geometry. They come from geometry. OK, so let me talk now finally to move to the discrete version. So again, remember, I'm back to the coins. Now think that I'm in the situation of the coins. You remember I asked you, what's the fewest number of coins that you need? Or I asked you about the fewest number of the different denominations that I need to represent this amount of money, right? OK, so I want some kind of discrete version of Carathéodory's theorem. And things get hairy, because this is number theory now. So first of all, there's no cones anymore, because I'm interested on integer linear combinations. So I'm interested on linear combinations that are non-negative and integer. That's what I need to have. So that defines a different animal called the semigroup. The semigroup, again, given a finite set of vectors, or even an infinite set of vectors, you can, I'm always working with finite, but let's say you have a finite set of vectors, you have a matrix, the columns of that matrix, and you take integer, non-negative linear combinations of these T vectors, OK? So that defines all possible finite such combinations defined as semigroup. Now clearly, the semigroup is inside the cone, right? Because these are special points in the cone. So the picture that you should have in mind is that if you have a semigroup, so for example, if I take now these 4 vectors, they're in 2 dimensions, they generate a 2-dimensional cone, which you see here. These are all the points that are in between these 2 lines. But now, what are the integer vectors there? What is the semigroup? The semigroup looks really weird. For example, we have all the integer solutions, or the integer points, all the points with integer coordinates that are above the line y equals 1. But every single point on the line y equals 1 is missing. For example, 1, 1. Can anybody write 1, 1 as an integer non-negative combination of these? Impossible, right? Impossible, because the second coordinate in all these generators is either 0 or bigger than 1. So you cannot, but nevertheless, you can write them as a rational, right? As a rational solution. So therefore, these points are in the cone, but they are not in the semigroup. Do you see the difference? So what makes number theory so difficult is there's all these weird situations, like gaps happen. Now, I'm not the first to look at this problem. So David Hilbert was really the first person who actually studied these three objects together. So the first one that he studied really was cones. He studied cones. Carathéodory and Hilbert were best buddies. I think actually Carathéodory considered Hilbert his mentor. And yeah, so this is really something that Hilbert was interested, the cone. Now, there's an object in between the cone and the semigroup, and this is an extremely interesting object, which is take the cone and consider all the lattice points that are inside the cone. Dump the gaps. So forget there are gaps. Just take all of them. So in other words, in the previous example, the intersection of the cone with the lattice points will be every single lattice point. No gaps. No gaps anymore. Everything that you see inside the cone. OK, and finally, the semigroup. And Hilbert was fundamentally interested on the differences between these three mathematical objects. So essentially, well, we know that the cone contains the other two properly, but the fundamental question that Hilbert was really interested is to understand when the semigroup is actually equal to the set of lattice points of the entire, all the lattice points in the cone. There's no gaps. The situation of all no gaps. And in fact, so in general, so you have these proper containments, right? The semigroup is properly contained in all the lattice points, which is properly contained in the cone. And yes, for example, if you go back to my favorite example of the 3x3 magic matrices, you can write every magic matrix as a real combination of the 4 that I gave you, but if you try to write as an integer combination, you are not going to be able to do it. The semigroup they generate is incomplete, has gaps. Here is a gap, 1, 1, 1, 1, 1. This is a gap. You cannot write this animal. But on the other hand, and here is what Hilbert proved, and this one is known today to PhD students taking qualifying exams as the Hilbert-Basis theorem, is that every pointed cone, every cone like the, well, don't forget about pointed, every nice cone, you know, pointed means nice. They're nice. So every pointed cone has a finite set of integer vectors in the cone that generate every single lattice vector in the cone. This is Hilbert's contribution. The proof is absolutely beautiful. I always ask it in qualifying exams. Hint, hint, hint for the students. So, all right. So, okay, so this is the Hilbert-Basis theorem. Now we have, you see, we had a cone which generalized vector spaces. Now we have Hilbert-Basis that generalize the idea of generating cones, but because we're doing generation, Diophantine generation now, right? All right. Open problem for the young people. I don't know the Hilbert-Basis. This is known the Hilbert-Basis of the 7x7 magic squares. I don't know. So can somebody crack it? Can somebody tell me the asymptotic? For example, how this grows with n? You know, you know, I can give you a paper if you want to know more. All right. So let's see. How am I doing on time? How about? Oh, okay, I'm good. Okay. So this is the. Yeah, so let me talk to you first, because I really want to drive into your mind, especially the young people's mind. There's so many open problems in mathematics. You know, even if we give you 100 problems to each of you to work on, you wouldn't finish, you know, exhausting half of what is open out there, right? So here is one particular question. So Hilbert, again, he says, well, every cone, I can find the Hilbert-Basis, so there's no gaps. So I have a generators. Well, how few generators do I need to write a vector, right? Remember my question for optimization applications? I need to know the minimal representations in terms of the Hilbert-Basis. Okay, if I do that, in 1986, these three gentlemen discovered something remarkable, that if you have a Hilbert-Basis of a d-dimensional cone, you need no more than 2d minus 1 vectors to express any vector whatsoever. What does this remind you of? Carathéodory's theorem, right? This is the version of the Carathéodory's theorem over the integers that Hilbert essentially suggested has to exist. But this is the first bound we got that is really good. Hilbert's bound was horrible. So this is really the best linear bound. And notice how close it's getting to Carathéodory's theorem. Carathéodory's bound was D. If you're in dimension D, you need only D vectors at most. And here is another one. In 1990, Andrasevo, Hungarian mathematician, he proved that the minimal, so you never need more than 2D minus 2 vectors in dimension, if you are in dimension D. Okay, so what do you think? Is it going to be D? Well, it's false. And this is one of the things that I really also like about mathematics. So when you think something is, this is going to be a theorem, some crazy counterexample comes out and shows you that you're completely wrong, that your intuition was completely wrong. Of course, the counterexample that these wonderful people found, Bruns, Gubelatze, Heng, Martin, Weismantel, they published this counterexample in 99. So this counterexample is in 6 dimensions. It's a 6-dimensional example, which they found through computers, which again brings me to a piece of advice for young people. Don't be, you might think that you will never use computers in your work. Just learn to use them. I mean, they're extremely, extremely, extremely useful. They're going to save you time. They're going to give you intuition. They're going to be your friends. Trust me. So, okay, so here is another open problem for the young people. Can you prove, so what is what is the correct bound? Right now, there's a counterexample that shows that the bound has to be between 7/6 of D and 2D minus 2. So it's incredibly close, but we don't know what the right answer is. So yeah, open question. Okay, so I have to talk a little bit about other things. So let me just say the following. So of course, I always say, when you see a red Ferrari, you say, oh, I want a car like that. So when I saw these theorems, I said, oh, I want a theorem like that. So I really, it's like you see this theorem that is so unbelievably beautiful that you want to get a theorem like that. You want to just work on that. So I'm going to tell you our contribution. Our contribution is, so what happens if you have gaps? So as I told you, life has, so bad things happen in life, so there's gaps. Sorry. Hilbert told you the best possible worlds is possible, but you might not be there. So what happens in that case? And the bad news is that in that case, it's going to be impossible for you to give a bound that only depends on the dimension. So Carathéodory's theorem, Carathéodory's dream is broken. It's not going to be true. And I'm not going to go over the details of why, but so there's an example. There's an example of a specific point configuration that if you try to bound in terms of just the dimension, you're going to get crap. It's not going to work. So, but here is our theorem, and it uses some cool stuff to prove this theorem is really, well, I wish I had time to tell you more, but so the theorem is the following. If you call gamma the largest entry, the size of the largest entry in the semigroup generators, so you have the semigroup generators to begin with, and you look at the largest entry there, call that gamma, then you can guarantee that any element of the semigroup can be written by a linear combination of length no more than 2D log of 2, square root of D times gamma. So there's this bound that we prove. Again, it depends on the size of the entries. I mean, if you promise me, Jesus, I swear, pinky swear, I'm never going to use more than entries of size 1, zeros and ones, for example, then this becomes just depending on D, but it's not. All right, so let me just move to, I think this is, yeah, and this theorem has direct applications to the description of the structure of optimal solutions in integer programming, in integer optimization. Now you can tell how many zeros are there in an optimal solution. And it's given by the bound that I just described. That's it. This is the bound that I gave you, and the sizes of the entries matter. Okay, so this concludes this part of my talk. I was asked by the organizers to bore you with a little bit about me. I hope don't put you to cry. Let me just get my slides here. Okay, I don't know who said this quote, but it's a quote that I have in my office, kind of in the door of my office. And it says, anything that a man has to say that it really matters, that is worth saying, is really an expression of his love. And, well, I hope you saw that I like this topic. It's really, so a little bit about myself, of where I come from. Oops. Oh, there you are. So that's my origin. This is my family. That's me, my dad, my mom, my little sister. So I was born, as Ulrika say, I was born in Mexico for a middle-class family. I was, we were the only children. It was a relatively small family because all the brothers of my father had 7 and up children. So we were the small family. And I was the first of the side of my family, for my father, the family side, to go to college and to finish college, because several people tried before me but didn't make it. And I mean, all I want to say is that I wouldn't be here without my mom. I mean, just my mom, in many different ways. She's a remarkable woman. In particular, for example, she had to raise us alone most of the time, because after this photograph was taken, they divorced, and it was bad. But anyway, I'm not going to bore you with that sad story. So in the 80s, I started at the National University of Mexico. And I'll tell you one story about my father, because that relates to me going to college. So my parents divorced. They were just always fighting, and he didn't want me to study mathematics. He told me, if you study mathematics, you're done with me. I don't want to talk to you. So he was very adamant that I had to make money. So he told me, I'm not going to talk to you unless you study something else, because he thought I was wasting my opportunities. So you may not know this, but in Mexico, so the admission to the National University, I mean, you don't pay tuition, really. I mean, you pay a symbolic tuition, but it depends on your grades. So I had grades good enough to go in anything that I wanted, like medicine or law, all these wonderful careers that will make tons of money. So my father really thought I was crazy, right? So yeah, so anyway, when he said, you are not going to study math, I said, watch me, So anyway, so I went to there, and I was, from the very beginning, I kind of, in retrospect, I was this strange kind of guy, because, for example, see, this is, by the way, this is my photo the day that I defended my undergraduate thesis. I said, undergraduate thesis defense. Can you believe this? Anyway, so this is the undergraduate thesis defense day. This guy is a representation theorist and algebraist. This guy is a geometry topologist. This guy is the founding father of Mexican combinatorics, Victor Neumann Lara. He single-handedly founded combinatorics in Mexico. I mean, like, he came back from France, started teaching people combinatorics. That's it, right? He's the guy. And then this gentleman is one of his students who he did incredible mathematics, but he became very well known in Mexico because he was the director of the National Bank. So he also was very influential to me. So these four people were, this is exactly what I am in some sense. Well, I mean, not all of them, but I have pieces of them in me because, first of all, I love geometry, as you saw. I love algebra, and I love combinatorics, but I also love economics, modeling, applied problems. This really ticks me. It's like really, and this has been forever, right? Ever since I was an undergraduate. So anyways, I used to go see him for talking to him in the National Bank. It was kind of an experience. If you are ever in Mexico City, go check the National Bank building. It's an amazing historic building. Anyway, in the 1990s, I moved to Cornell University in upstate New York. Looks beautiful, but when it's winter, it's miserable. Anyway, so I went there. I did my PhD in Cornell in applied mathematics with a minor in operations research. Raise your hand if you have heard of operations research. Okay, so some people have not heard of it. If you are a math major, I invite you, I urge you, please check in Google what is operations research, because it's a part of applied mathematics that is very different from what you normally hear about applied mathematics in the undergraduate curriculum. And it's extraordinary. It's combinations of discrete objects, algorithms, probability, statistics for the design of logistics and planning. So this is really exciting. Connects to economics as well. Anyway, that was my minor. But my PhD advisor is a guy that is well known because he's an algebraic geometer. So this is Bernd Sturmfels. He's another, I have a lot of him in me. He was a very influential guy. The first thing that he did is actually take me as a student, which is, a great honor. And I don't know how I deceived him, but he took me, and then I finished in 95. And by the way, I cannot stops to say that Eve and I were office mates, essentially, right? So we were in the glorious Center for Applied Mathematics. And that was a fun time. Yeah, so then I took my first job at the University of Minnesota, another tropical place. Jeez. And my second job was at the computer science department in ETH in Zurich, in Switzerland. Boy, that was also very cold. Well, finally, you know, when I got a job in California, I immediately accepted. I didn't even look at the salary, right? It was like, yes, 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 whatever. Yeah, so that's more or less the story. But now I'm going to tell you about my greatest achievements. These achievements easily should be nominated for the Nobel Prize, for the Fields Medal. And I will say that my co-author has been a really incredible co-author and friend for 28 years. So this is my co-author, Dr. Ingrid Bruce Masher, my wife of 28 years. And these are our two children. Antonio, he graduated from LMU, very proud of Go Lions, right? So he graduated here from Loyola Marymount in Los Angeles with a degree in film production. And he's a writer right now. He's an activist. His film about undocumented, migrant children in California, the lives of migrant children in California, got accepted to be shown at Cannes. And so he likes to talk about the stories of Latinos and Latinas. This is something that, and well, Hilbert can tell you how troublemaker he is. Thank you. So, and then our youngest son, Andres, he's an economics major in Harvard, and he likes math a lot. He doesn't admit it, but you know, secretly, I was very happy that he likes economics too, because we always are talking about models and fixed point theorems and things like that. So it's cool. It's cool. And my wife is a biophysicist. She directs the microscopy facility in the veterinary school at Davis. Okay, and these are my other children. I want to talk to you especially about these other children. These are some of my PhD students and one of my former undergraduates. So from here, this is Eddie, just got tenure at the University of Wisconsin-La Crosse. David, he is a staff member at IBM Watson in New York City. Susan just got tenure 2 days ago from the US Naval Academy. Terrell is an associate professor now, yes, tenure as well in University of Wyoming. And Rudy was my first PhD student. She got tenure at the University of Kentucky, recently moved to the Naval Postgraduate School. So I don't know what the Navy has with me and my students, but 2 of my students work for the Navy. And actually, I'm very proud to say that I'm a grandfather now, academic grandfather, because she's had now 4 PhD students in statistics. She's a professor of statistics. Here are some of the younger people. So I want to tell to the people of UCLA, this is Jamie Haddock. She's coming as a postdoc to CAM. So watch for her, okay? She's great. And here we are in the, this is Jake. They both got the teaching awards at Davis that year. I'm very proud showing their award. Now, Mohammed is a professor at Harvey Mudd College, and I want to say something remarkable I think he's doing. So, see, I never agree with my father in many things, but he taught me many little things. And he says, before you get into a fight, just plan for the fight. I mean, just know where you're going to hit, know what you're going to do. And I was telling this story to Mo, and I want to believe that he understands this, because you know what he did? People, listen to this. GREs are by far, in my opinion, one of the reasons Latinos, Latinas do not get admitted in graduate schools by far. It's one of the single-handed reasons, because we are anal about the importance of the GRE, right? So it's so important. Okay, so first of all, if you are going to take the GRE, prepare for it, right? Number 1. Now, since we know it's a problem for our community, that because these standardized tests are not working so well, what you have to do is prepare. So when Mo took the initiative to start preparing people for the GRE, like he really has online material, he wrote articles, what is the best strategy to prepare for the GRE? It's not rocket science. It's not rocket science. It's just a matter of organize yourself and prepare. And he's leading the way on making a significant difference by knowing where to hit. The GRE is where to hit. Okay, so these are my undergraduates. I just want to finish because I'm over time. I love my undergraduates. These guys are working on oriented matroids. That's why they're showing this. It's cool math, trust me. They're not just making snowballs or something. And I'm very happy to say that over 30 of my undergraduates have gone to graduate school. And actually, I just talked to her. She's now the MESA director in Sac State. So she's in charge of the Mexican-American students in Sacramento State University now. Now, as a faculty, as a staff member, she's going for her PhD in education. And this guy's finishing his PhD in statistics. Okay, so final 10 things. So do not forget that mathematics is beautiful and fun. And you might be one of these persons that, oh, I love math for the fun and beauty. I don't want to have anything to do with reality. There are famous mathematicians that say this to you, right? That's fine. Okay, if that's what you want to do not forget, nevertheless, that math is also powerful and useful. And vice versa. If you only want to do math because it's powerful and useful, you're also biased. You know, the diversity of gender, diversity of subject is also important. Diversity of mind, of how you approach mathematics is important too. Yes, there should be no difference between pure and applied mathematics. Math research is alive. Do not feel that you are never going to find an open problem you can solve. You will find one cool open problem and you'll solve it. And computers will help you if you just let them. Math is not a spectator sport. You know, don't take this abstract attitude that, oh, you know, I'm just going to read the book. You know, just get your hands dirty. I invite you to really calculate, study examples, to really get your hands dirty. I don't know who said this, but it's a cliche maybe, but I really think it's true. Success in mathematics is 5% inspiration, 95% perspiration. So be passionate. Love what you do because you're going to spend a lot of time doing it. Yeah, so math scares a lot of people. But it should really be the case that math is accessible to everybody because anybody can do math. And so that brings me to this piece of advice. Try to be of service to others. Bring them to mathematics. Be kind and generous. Do not be a jerk. I think that's a good advice. Yeah, I'm not shy to say, you know, I have pretty good papers. I have some very nice books. But the most important contribution I will ever make is the people I have trained. This is by far, I'm sure. So I just end by saying, please try to live a healthy, balanced life. Bye.